Hello, my name is Dirk Smith of Ionix Gas Technologies. The video you are about to see, Static Electricity in Polyethylene Gas Pipe Hazards and Controls, is a class I've taught over the years to association operations meetings, company safety meetings, and state pipeline safety meetings. Ionix Gas Technologies has developed a suite of products to eliminate static both inside and outside polyethylene pipe. This course is the result of the calls that we have received about the nature of the ignitions that customers had. Over the years after receiving these calls, we noticed a pattern emerged of where these ignitions were occurring. So this class is designed to highlight those hazards and then offer suggestions of controls for those hazards. The first slide you see here is a shot from AP in Hanoverton, Ohio in 2011. Tennessee Gas Pipeline runs through this countryside, and the night sometime the pipeline began to leak and it ignited. Material failure analysis will determine the cause of the leak. But the question that's never asked afterwards, and is the most important question, is what caused the ignition? This pipeline was in remote countryside. There was no weather reported that night. It was still air, 29 degrees. What was the ignition source? Because a leaking pipeline like that doesn't cause any damage until it ignites. The next slide you see is a random year we picked from the Office of Pipeline Safety, pipeline incidents. And what we wanted to do is compare and see, is there a statistical difference between the number of flammable liquid pipelines, that being diesel, kerosene, crude oil, that leak and ignite as opposed to natural gas pipelines. And to make the analysis a fair one and a statistically valid one, we had to do two things. First of all, we made sure that we picked incidents where there was no known ignition source. That is to say, after the investigation was done, they could not determine any known ignition source. And the second thing we did is we wanted to make sure the pipelines were in similar physical locations. That is to say, we only chose incidents of pipelines that were in right-of-ways. We didn't choose pipelines that were on bridges and compare them with pipelines that were in the ground. So of these incidents on this slide, all of them were in-ground, in right-of-way pipelines with no known ignition source. And if you take a look at it, there's a startling statistical difference. Of the 88 pipelines of liquid flammable materials that leaked, only 2 of them ignited. On the other hand, there were less natural gas pipelines that leaked, only 48, but of them, 41 ignited, resulting in 8 injuries and 3 fatalities and 8 explosions. So the observation of this is, all things being equal, if a natural gas pipeline leaks, 75% of the time it's going to ignite. Whereas if a liquid flammable pipeline leaks, less than 5% of the time it's going to ignite. So the real question is, at this point, the focus of pipelines and safety has generally always been about damage prevention. The purpose of this course is to understand the cause of the ignition of the damage. The problem isn't so much understanding how or why piping is damaged. The problem is controlling why it ignites. The purpose of this course is to fill that gap, to start to explain the reasons why pipelines, when they're damaged, ignite. I hope this video will be helpful to you. The first thing we're going to do is to talk about some presumptions as we begin the course. We have 2 goals in this course. First is a broader goal, is that we want you to learn to identify known static ignition risks in your systems. By understanding some of the basic principles of static electricity in polyethylene pipe, you will be able to educate your field people to recognize a potential static ignition risk before it occurs. The second thing we want to do is to be able to teach you enough about static electricity so that you can go and evaluate your own static suppression procedures to make sure that they're adequate and they're effective. When we go out and talk to people, we find some gas companies have no procedures whatsoever and some have very detailed procedures. Whatever the case may be, we hope at the end of this class you will then be able to look at your operation and make sure that you have sufficient static suppression procedures for those known hazardous ignition risks, and 2, that those procedures are effective in eliminating the static in that procedure. There's 2 presumptions we make here as we go through this, and I want to deal with them very quickly, and then we'll go on to understanding static electricity. The first is that static electricity is a known and researched phenomenon in the gas industry. I have some people that think you can't understand static electricity. It just shows up when it shows up. It's a black art. Nobody can understand it. That's an urban legend. As we go forward in this, I'm going to give you your industry's research about static electricity and polyethylene pipe as the basis to understand static suppression procedures. The second thing is, we want you to understand too that your research organization has said that static electricity is a problem for all gas distributors. I have some distributors say they deny they have a static issue. I have some that seem to be in fear of static. Once again, a middle ground is probably most appropriate. Here's what your research organization said about static electricity and gas operations systems. As the use of polyethylene pipe for gas distribution lines increases, the safety issues relating to electrostatic discharge of PE pipe during repair operations continue to be a major concern to the gas industry. Static electricity in polyethylene pipe is systemic. It is in all systems. It's not a matter of bad engineering, bad operation, poor operation of your system. It's basic physics, as you'll later see. So it's important not to deny the problem. It's important not to overemphasize the problem. And one last thing. Most of the issues with polyethylene gas pipe are dealt with local distribution companies simply because they have so much polyethylene pipe transporting gas. However, the principles in this class are applicable to anyone who transports natural gas through polyethylene or plastic pipe, whether it's producers or gatherers. I've had calls and problems from them, midstream operators in their use of plastic pipe, or LDCs. Anyone who is transporting natural gas through a plastic pipe, whether it be polyethylene, PVC, or anything else, the principles that we're going to talk about today are equally applicable. So, with that, we'll move to our next section. As we start to move into our class on static electricity and polyethylene pipe, the first thing we have to do is make sure we're all using the same terms and we all understand what those terms mean. And the first term is static electricity. What is static electricity? Sometimes when I talk to people out in the field, they seem to think that static electricity is different than the electricity in their homes, for example. Electricity is electricity. What makes static electricity different is that static electricity is so called because it's an electrical charge at rest because it resides on an electrical insulator. Electricity is electricity. Static electricity is electricity that for some reason has developed and it's sitting on a material that will not allow it to conduct away. Therefore, it just builds up in a particular spot. There's certain materials out there that are conducive to preventing electricity from moving. We call those electrical insulators. Polyethylene is one of the materials that resists the movement of electricity on its surface. So if for some reason electrons start to pile up and build up, they just sit on that surface. They can't move. They're static. So that's why that electricity is called static electricity. The electricity in your home, which moves through wires, is called current electricity because the electrical charge is sitting on material, copper, that allows the conduction of electrons. So static electricity is so called because it's an electrical charge that is sitting on a piece of material that will not conduct electricity and it can't move. It's static. Well, then the next question is, what causes static electricity? Well, static electricity is caused by the friction of one electrical insulator against another, and it displaces electrons and they accumulate on the surface. So in the case of natural gas in polyethylene pipelines, you have plastic, which is an electrical insulator. You have methane gas, which is an electrical insulator inside it. And as the methane moves through the pipe inside the pipe, friction is caused by that pipe, in that pipe, by the gas moving through it. And that static charge, these electrons get knocked off the methane molecules and they start to accumulate in certain places on the inside of that pipe. So it's friction that causes the placement and the creation of static electricity. And in the instance of natural gas in polyethylene pipe, it's the flow of natural gas, methane, inside the polyethylene pipe that creates the static and builds up the static charge. Well, so what? I mean, there's static everywhere. So what? Well, here's the problem. Mother Nature doesn't like electrical imbalances. The physical world is intended to be at electrical neutrality. In the summertime, when the hot air rises and then it cools off and drops down again, what will happen is the friction of the air going up and down causes static electricity, and sooner or later, those electrical charges will want to go to electrical neutrality, and in the summertime you have lightning as those electrons, that static charge in the cloud, arcs the ground to neutralize each other. Well, the same thing's going to happen inside your polyethylene pipe. If static electricity builds up, Mother Nature does not like electrical charges. It wants electrical neutrality, and it will remedy the situation. It will arc to ground sooner or later to relieve itself of the electrical charge unless you do something to prevent it. And that arcing, in the case of natural gas pipelines, will either lead to an ignition or to a pinhole leak in your pipe. So it's because that Mother Nature wants to be in electrical neutrality and that static charges build up inside your pipeline that you're forced to deal with this issue, or Mother Nature will take care of it itself. There are four basic principles of static electricity in polyethylene pipe. The first one is this, that all static starts inside the pipe. As we said, static electricity is caused by friction, and the only friction in the system is the passage of methane gas inside the polyethylene pipe. As the methane runs inside the pipe, it rubs against the walls of the pipe, and it knocks loose little electrons from the methane, and they accumulate on the inside walls of the pipe. This is the root cause of any static ignition problem you encounter. If you don't remember anything else from this course, remember this first and most important principle of static electricity in polyethylene pipe. All static issues that you have ultimately are root caused inside your polyethylene pipe with the passage of gas inside the pipe. This is not my opinion. This is what your industry research company has said. When PE pipe is charged by dust or particulate flowing in the gas turboelectrification, charge is generated initially in the interior of the pipe. All static starts inside the pipe. Now, how do you measure static? Well, this next slide is a picture of what's called an electrostatic locator. You don't have the senses to detect static electricity. You can't see, smell, taste, touch, feel, hear static electricity. We don't have the sensory capacity to determine if static is present. So you need an instrument, a meter, to detect static electricity. And this is one of the meters that we sell to our customers. There's a little sensor in the top, and what it does is if there's a pile of electrons that have accumulated on an insulator like polyethylene pipe, those electrons throw off an electromagnetic field, and the sensor determines their presence, detects their presence, and deflects the meter. What we're going to do is just show you in this next video how static electricity is generated and how you can measure it on a piece of pipe. As you see this pipe here, we have the electrostatic meter mounted on top pointing down and a piece of polyethylene pipe. And as I rub the pipe, you'll notice that the static meter starts to indicate the presence of static electricity and it deflects the meter. I then spray the pipe with our aerosol static suppressor, and you notice the static is then gone, indicating that we have dissipated the static on the pipe. The point of the illustration is to show you how easily it is for static to be generated on polyethylene pipe, and that really you need a meter to determine its presence. Now, I have people that ask me, operators say, well, should every guy have a static meter? And the answer is no. Every standards department ought to have one electrostatic voltmeter on hand for measuring purposes. However, you want to presume, and your industry research says, that you need to presume that there's static in your system. If you have your procedure contingent upon your field people making a measurement with an electrostatic voltmeter, that's a very problematic thing to do. If they don't know how to do it, reading static's a very difficult thing to do in the field. You really need a lab environment to control your surroundings in order to get an accurate reading. And you wouldn't want a guy who misreads it and thinks there's no static, and you wind up having an incident on your hand. So you should always presume that static there. However, a static meter is good for any operations department just to keep on hand in case they do need to measure some static. The second principle of a static and plastic pipe is this. Once static is generated or created, it just doesn't go away. It will not conduct away because it's sitting on a non-conducting material. That's why it's called static electricity. It's on a material, it just sits there. So static electricity, once it's generated in your system, it's just not going to go away because you wish it away. It's going to stay there until it dissipates itself or you purposely get rid of it. Here's what your industry research company has said. Charges imparted to the interior PE pipe surfaces act as point sources and are immobile because of the high inherent resistivity of PE. In other words, what they're saying is polyethylene pipe, because it's a superior electrical insulator, when that charge gets built up, it's just going to, in the interior of that pipe, it's just going to sit there and it won't go away until you do something about it. The third thing is that static electricity is induced on the outside of the pipe. Now, that's why you do the external static dissipation. Remember, we said static always starts on the inside of the pipe. It stays there. And what your industry research says is that interior static induces or creates a charge on the outside surface of the pipe. Now, I can explain in physics why that happens, but it's beyond the scope of what's necessary for you to understand. All you need to understand is that the static charge that you have on the outside of the pipe is caused by the static that's on the inside of the pipe, and that you need to dissipate the static on the outside of the pipe. Here's what your industry research organization has said. The electric field resulting from the interior charge induces exterior charge on the pipe. Finally, the fourth principle to remember about static electricity and polyethylene pipe is that static will arc. Static electricity just won't go away. Static charges will arc and ignite a gaseous mixture if the interior static charge is exposed to ground. Here's what your industry research company has said. The interior charge problem is still evident after gas flow has been cut off and a defective section of pipe is cut for repairs using a saw or circular cutter. When a metal object penetrates the inner wall of a charged pipe, a spark discharge is inevitable. It's not probable, it is inevitable. So, here's a summary of how the Gas Research Institute, your research arm, says is how gas ignitions occur. If there's an ignition of leaked or leaking gas in the absence of a known ignition source, given that the passage of natural gas inside a pipe creates static, the most probable cause of the ignition is that static electricity is arced to ground in the presence of a gaseous mixture. That's the paradigm. That is what's occurring when you have a static ignition. The root cause is the static electricity that has been generated on the inside of the pipe. This means that you have a unique problem in distributing natural gas in polyethylene pipe. It creates its own ignition source. This next video you're going to see was broadcast in 2001 in Oklahoma City by the Evening News. And I apologize in advance for its quality. It was broadcast over the air, and a friend of mine recorded it on his TV as it was broadcast. So the quality is quite grainy, and the audio is difficult to hear. But essentially, here's what happens. A gas company is called out because of third-party damage, very typical, and they arrive on the scene to find gas blowing out of a third-party damaged line. They're there repairing it, putting a repair clamp on it, when all of a sudden, while they're working on the pipe, the gas ignites on camera. And you will see the guy scrambling to get out of the way as it ignites. The question, again, just like before, is not how the pipe got damaged. The more important question is, why did it ignite? You had a trained crew there who would not use any sparking or flammable or materials or procedures that would cause a spark. And yet, while they were working on it, the pipeline ignited. So as you watch this, ask yourself that question: what could have caused the ignition?
A natural gas explosion rocked an Oklahoma City neighborhood just before noon today. Workers were trying to repair a ruptured line at Northwest 131st and MacArthur when the gas ignited. Newsline 9's Heidi Browning joins us live from that neighborhood. Heidi?
Well, Kelly, there's a bit of a mess out here in the neighborhood. You can see behind me what's left of a fence, charred remnants of the posts, and quite a lot of digging that's been done to make repairs to those lines. But people coming home this evening will find a much calmer scene than what many people saw this morning. It started as a fairly routine repair job. O&G workers were trying to get the gas turned off after a 2-inch medium pressure line was accidentally cut. Suddenly, the gas exploded, sending huge flames into the air. 2 workers received minor burns. O&G officials say there's preliminary speculation that static electricity in the plastic pipe somehow caused the explosion. It took about 30 minutes to control the fire and get the gas turned off.
So as you see, what the Gas Research Institute says is correct. The paradigm is correct. It's static electricity generated inside the pipe that causes the static to build up. It eventually overcomes the insulating, what they call dielectric properties of the air. It arcs the ground in a gaseous mixture, and you have an ignition. So here's the fundamental reason why you have a standard operating system procedures for static suppression. Since gas moving inside pipe creates its own ignition source, you need to focus on preventing the cause of the ignition of the leak as much as the prevention of the leak itself. Now, up until this point in time, the only procedures that the natural gas industry had for dissipating static was very crude grounding using soapy rags. That was originally developed and recommended by the American Gas Association about 25, 30 years ago when plastic pipes started to come out and they were having static issues. Since that time, there have been great improvements on anti-stat technology, and some of those advances are incorporated in our products which we bring to market to dissipate static. But most companies still use what's called a soapy rag or wet rag grounding method to dissipate static. And there's a couple problems with that. The first thing you need to be aware of is that first, when you're using soapy rags or grounding to dissipate static, you are essentially putting your workers in close proximity to an ignition in order to get rid of the ignition. In other words, here you are, you're going to put soapy rags to dissipate a static ignition. They've got to touch the pipe that could arc to ground and cause an ignition in order to get rid of the static. The second thing is that when you use soapy rags, you really can't determine if they're effective. What I mean by that is this. Soapy rags and grounding create an electrical circuit. You wrap wet rags which conduct electricity, you put a conductor on it, and then you ground it. You're assuming that there's an electrical connection. In other words, the rag is wet enough, the electrical wire is not broken, and you got a good ground. You have no way of knowing that. You presume that's the case. But there is no visual way you can tell if you have a grounding circuit on those wet rags and ground rod. And finally, wet rags will do nothing to eliminate static on the inside of the pipe. Think about it. You have polyethylene pipe and it's containing methane gas under pressure, what makes you think that if you put wet rags, soapy wet rags on the outside of that pipe, that somehow or another that's going to dissipate the static on the inside of the pipe? Of course not. And your research organization has said that will not solve the problem of static inside the pipe. And it's very, very important that you understand that you're not led into a false sense of security that simply because you have put wet rags on the outside of the pipe that your static problem is finished or is dissipated. Here's what your research organization has said. Prior to this project, safety procedures involved wrapping the pipe with wet soapy burlap. This procedure is effective for neutralizing exterior charge accumulation, but does not affect the interior charge of the pipe. Our aerosol static suppressor is a topical anti-stat, and you can apply that remotely so your people don't have to get near the static charge in order to dissipate the static charge, nor do they have to ground it for our product to work. So as we have these four basics now of static electricity and polyethylene pipe, we now can go on and take a look at the most hazardous operations that you will encounter as operators of natural gas in polyethylene pipe. Now that we understand the four basic principles of static electricity in polyethylene pipe, we can apply this to the particulars of distributing natural gas in a plastic material. Most people, when they think of static electricity in polyethylene pipe, only think of it as an ignition or safety issue. In reality, static electricity in polyethylene pipe causes two problems. The first one is an ignition risk, but the second is an integrity issue. Static electricity puts electrostatic holes in polyethylene pipe. So as we go through this, the first thing we're going to talk about are the 5 most dangerous static ignition gas operations. And then after that, we're going to talk about the integrity problem, how static electricity puts holes in plastic pipe. So first, the ignition risk of static electricity in polyethylene pipe. In order to have an ignition, there are 3 necessary components. You need to have a gaseous mixture of 5 to 15% methane to air. You have to have a sufficient static voltage. 3,000 volts is necessary to create 1,100 degrees heat during arcing that will ignite and begin the methane oxidation. And finally, you need proximity to electrical ground. In other words, that static charge has to arc to ground. So the instances that cause your significant ignition risk possibilities must have these 3 conditions present. When we've received calls from customers, we find that there have been a pattern to the incidents that we were called about. And the first incidents that we have so many calls about and notice that it's most dangerous and the most problematic operation that you have is probably not a surprise to you. It's third-party damage. As you see in this slide, next slide, you have a typical operation where there's a piece of pipe and it's been dug into and there's a breach in the line. Because we know that static electricity is formed by friction inside the pipe, those little red spots indicate random places where static is present inside that pipe, where static electricity is accumulated inside that pipe. Now, if it happens that that third-party damage digs into the pipe at a place where there is a hot spot of static inside the pipe, since the pipe is now opened, there's a gaseous mixture around it, there's static electricity there, and it now has proximity to ground. In other words, you've opened the pipe up and it can arc to ground. You find this is a very dangerous situation. Sometimes pipelines will ignite when they are cut. They ignite simply because what has happened is when the third party dug into them, they happened to dig into a hot spot of static inside that pipe, and conditions were right where it ignited immediately. On the other hand, you may have a situation like that video that I showed you a little earlier, where when the pipe was breached, they didn't dig into a hot spot, and so the pipe blew for a certain amount of time until the static electricity built up so high on the open edge of the pipe that it arced to ground and ignited the gaseous mixture. So you really can't predict if a pipeline, when it's breached, if it's going to ignite immediately. But you understand that as that gas flows out of there, in the turbulence around that break, as the gas flows and there's very turbulent conditions around the break in the line, static builds up on that edge and on the inside edge of that pipe. And if the static charge eventually gets large enough, it will arc to ground and ignite the gaseous mixture present. So these third-party damage situations are extremely dangerous and problematic, and it's very difficult to predict if and when they're going to ignite. But you have to understand that what's occurring, it is that static electricity building up on the inside edge of that pipe. That is your problem. So what we tell our customers, if they have a third-party damage, they have two ways to deal with that. First of all, if it turns out that you're able to squeeze off the gas flow, then what we tell our customers is don't let anyone into the pit until the static has been dissipated. In other words, we have an aerosol. Here's a picture of our aerosol reach tool. What they do is our customers take this tool and they put our aerosol on it, and from outside the excavation, what they're looking to do is we tell them to spray into the break, into the cut, because remember, all the static starts on the inside of the pipe. So you don't want anybody to get near it. You want to spray that inside the cuts before somebody goes down in the excavation. And then after you spray the inside of the cut, you want to spray the outside edges around it, around the broken ends on the outside of it. The most important thing to remember is do not assume that it's safe to enter an excavation simply because the gas flow has been cut off. Remember that static electricity, once it's created, just doesn't go away. And you put somebody down that excavation and they go reach there to put some soapy burlap around it, they may act as a grounding rod and ignite the gas that's laying in the bottom of that trench. At the time of this video, several months before this video, that very thing happened with very, very serious injuries to workers. So we tell our customers, don't go inside an excavation. After the gas flow is cut off, don't go inside the excavation until remotely you've dissipated the static inside the cut and then around the cut and around the edges. Now, you may have a situation, and it happens, where you can't shut off the gas flow. Then what we tell our customers to do is, again, take that reach tool and spray our aerosol static suppressor as close to the cut as you possibly can. Because again, the static is building up on that outside edge. Now the gas flow is going to want to push away any liquid or spray that's put around there, but at least you're getting some anti-stat in there that dissipates any static on contact. Our product's a topical anti-stat. It doesn't need to be grounded. It's not soapy water in a can. What it does is that on a chemical basis, it literally eats up static. That's what basically they do. And so when you have a situation where you have blowing gas and you have to put somebody in the excavation, you want to keep spraying and bathing that area where that gas is escaping with our aerosol static suppressor as long as you can until you brought everything into control. Once the situation is under control, anytime anybody goes back into that pit or excavation, you always remotely spray into the excavation before anybody goes into it. We had an instance where there was a repair clamp put on and everybody thought it was safe to go into. They went in the next day and there was static there because the gas was leaking around the clamp and it built up a static charge and it ignited when a tool was put to the repair clamp. Anytime a period of time goes by and somebody's going down in an excavation, you need to dissipate the static on that point before anybody goes into that excavation. When you look at the broad scope of operations you have, this is the most dangerous. This is where you have to be at most cautious and most prudent in your static suppression procedures. As we talk about some of the other procedures down the road here, they're less and less dangerous in the sense that ignition probably be a small one and the damage or the injury would probably be not as significant. But because of the nature of this, you cannot be too prudent when you're dealing with third-party damage and static electricity in an excavation where leaking gas can accumulate and static can build up. The second most dangerous operation is purging. When you think about it, Purging is just like third-party damage. You got a line that's blowing gas. Now in this illustration, you'll see that there's a grounded metal pipe, purge pipe on the end of this pipe. And everybody assumes simply because you got a grounded pipe and it's a metal pipe, it's going to be safe and there's no static. Not true. You can have metal pipe build up static charges when coatings are on the pipe, when debris builds up. Any place on that pipe, it gets oxidized or rust, you can have a situation where it's a non-conductor and static charges can build up. And again, just like soapy rags, you're assuming that there is an electrical contact to ground, but you can't prove that. You're assuming that. In the same way, you ground that metal pipe, you're assuming there's a circuit there. You have no way of actually knowing that's the case. So what we tell our customers to do when you're purging, even if you're using a metal grounding pipe, purge pipe, that you take our aerosol with a reach tool and you remotely spray inside the pipe. Remember, it's the inside edges of the pipe that's blowing gas is where the static is. Remember, static always starts on the inside of the pipe. And so we tell them to first go around the pipe and spray inside the pipe remotely, and then spray on the outside of the pipe, and then spray around the connection between the plastic pipe and the metal pipe before touching anything. Again, these can be very dangerous situations, and that's the reason we recommend you do this remotely. The third most dangerous static operation is plastic pipe squeeze off. And this is more of a shock hazard as opposed to an ignition hazard. We've had numerous reports of people who have been shocked due to squeeze off of plastic pipe operations. So we tell our customers this, is when you're squeezing off a plastic pipe, you need to spray the beginning and the end of the pipe, the area in front of the squeeze off and the area behind the squeeze off, before squeeze off begins to dissipate any static. And then after squeeze off is done, if you're going to handle this pipe, do the same thing again, remotely with the reach tool, reach down and remotely spray and dissipate the static in the front and the back of the area of squeeze off. I taught this class at a pipeline safety conference in Wisconsin, and I remember a guy coming up afterwards and he told me how he was a young guy in the field and they'd done a squeeze off, and he says there was a big explosion and boom, and he was knocked out of the pit. No fire, he could never figure out what it was, and he realized it was a static electricity during the squeeze off operation. This is very common, and therefore you need to treat it with respect and remotely dissipate the static using a reach tool before you squeeze off, and if you're going to touch the pipe afterwards, spray again before anybody touches it. The fourth most dangerous operation we've heard reports on is hot taps. What happens is when you attach the fixture and then you're drilling down when they're pulling the coupon out, remember you can have static inside that pipe, so if they happen to drill into an area where there's a hot spot when they pull that coupon out, they could hit an area and the exposure of the gaseous mixture could ignite. So what our customers do is what they will do is after they fuse the hot tap onto the pipe, they'll spray the inside of the tap with our aerosol static suppressor to dissipate any static present, and then what they will do then also is spray the tool. That way when they pull the coupon out and they're drilling, there's no static electricity that might ignite any leaking gas. Finally, the last most dangerous operations, and it's kind of a catch-all, but it's plastic pipe that's previously under pressure, removed from service and opened up, cut into or reached into. What we recommend these are it's kind of three things in one. So the first thing is if you're going to be cutting into pipe, what we recommend if you're cutting into pipe that's been previously in service, again, there could be static on the inside of that pipe. So what we recommend is when you're cutting into pipe, you spray our aerosol so it dribbles in and dissipates any static that might be conducted to the static that might be conducted through the tool and arc a gaseous mixture. We had an incident where customers of ours had taken a line out of service and their guys had cut through a stub line, and when they did it, there was an explosion. The guys were knocked off their feet and they thought they had an electrical line. There was no fire. It turned out what had happened is there were no electrical lines in that area. That what had happened is there was static inside the pipe, and when they cut into it, just as Gas Research Institute said, when their metal tool reached that static electricity inside the pipe, it grounded the pipe and grounded that charge, And the electrical shock knocked both these guys off, and they wound up going to the hospital. So when you're cutting into a pipe that's been in previous service, we recommend you spray into that cut. The second thing is, if you're reaching into a pipe, that you ought to spray inside the pipe. We had an instance where operators had cut a big, large diameter plastic pipe, set it aside, and for some reason the field workers had to reach inside the pipe. And when they did, their arm grounded a static charge that was residual on the inside of the pipe, and with methane that was laying in the bottom of the pipe, ignited and burned their arm. So everybody remember that Gas Research Institute says static charges on the inside of pipe just don't go away. And so what we recommend, if you have to reach inside a pipe, tell your guys to spray our aerosol inside the pipe to dissipate any static that's inside the pipe before they reach into it. And finally, if you're taking uncoupling or taking a pipe out of service, something out of service, and you're going to open up a joined pipe, we just recommend you just spray some of our aerosol on a band around the area it's going to be opened up, so you dissipate any outside static that's present, so when you uncouple the pipe, there won't be an ignition. It's important then, given these 5 most dangerous static operations, what you should be considering now is to evaluate your company's standard operations for static suppression. Focus on eliminating static where research has determined it resides in these 5 O&M operations. And in doing so, you'll drastically reduce the risk of an unintended ignition. In other words, these 5 operations, based on our experience, and my guess is you're going to find you've had the same problems in these operations. These are the operations you want to focus your attention on. These are the operations you want to direct your efforts to make sure that the procedure you use is effective and covers these areas. And by doing so, in this priority, by taking these 5 most dangerous and by making procedures that address the static risks in these procedures, you're going to dramatically reduce the probability that you're going to have ignition in this area. I remember a safety manager of a large utility company telling me he went through all their incidents, their damages and incident reports or workers' injuries. And he said that static electricity was one of the fewer incidents that occurred, but it was always one of the most costly. So by going through your procedures and start focusing on these, you'll wind up making a big dent in reducing any possibility of having static-induced ignitions. And the reason is because first of all, it's a risk base. You have now identified those operations that are the most dangerous. So you're focusing your areas and your efforts on static suppression on the areas where there's a risk. It's selective. In other words, you're not just firing a shotgun at everything. You're not spraying everything. All you're doing is you're saying these areas have known risks, and you address your efforts selectively to the known risks. And it's going to focus on eliminating the static risk in the operation and just not the means of eliminating static. And what I mean by that is this. As you understand the problems of static electricity, the principles of static electricity in polyethylene pipe, and as you understand the most risky static ignition risks, what you will do then is make sure whatever procedure you do is effective in eliminating static in that operation now that you understand how static operates. Let me give you an example. I had to talk to one guy and I asked him what his static suppression procedure was. And he said he says, I pour a bucket of water in the hole and pray like hell. Well, he may feel good about that, but let's say he's trying to dissipate static in a hot tap. He might as well sit and smoke a cigarette, because pouring a bucket of water is not going to do anything. He may have a procedure that he thinks is going to get rid of static in that hot tap operation, and it's absolutely doing nothing to eliminate the static risk in that operation. So what you want to do is you want to make sure that as you have identified the procedures that pose a static risk, that the method you use to eliminate the static is effective. It's effective. That's what you want to do. And the ultimate result will be is you will have a cost-effective static suppression procedure. you're not going to be wasting efforts on area where there's really not a static risk. On the other hand, you're going to be directing your resources, time, and training to those areas where you know there's a static risk. So in all ways, by understanding the principles of static electricity and by working through these procedures, then and making sure that you have an effective static suppression procedure on the high-risk operations, you're going to minimize cost and maximize your safety. So how do then we go evaluate your company's static suppression procedures? And first of all, like I said, you take these 5 most dangerous operations. You probably have procedures for most of these, but make sure these are covered. Now, you might need to add another procedure because everybody's company is different. You can't be slavish and just take these 5 that I'm giving you. For example, I got a call one time where there was a pigging operation, and I don't know it was in the launching or retrieving of a pig, but what happened is it was a plastic launcher, and what had happened is there was an ignition. Well, when you think about it, it makes sense. It's plastic, you've got an electrical insulator. Pig, you're going to have friction, gaseous mixture because they're, it's a pig they're retrieving or launching. And so what happened, they had an ignition and there were some injuries. So that company needs to have a procedure for static suppression in launching or retrieving pigs. So look at your operation. You know these 5 that I've given you are problematic, but you might need to add additional operations to cover the peculiarities, the particularities of your company's operations, and make sure you have a static procedure for problematic operations. The second thing is you want to make sure that the means that you're using to eliminate the identified static risk are effective. Once again, I'll remind you of the guy who poured a bucket of water into a hole. If he was trying to get rid of static in a hot tap operation, that won't work. The static's on the inside of the tap and on the top of the pipe and inside the pipe. So make sure that your procedure is going to effectively eliminate the static where it resides in the particular operation that you're attempting to dissipate the static. And finally, you need to be ruthless. You need to be ruthless in your enforcement of your procedures. I had an instance where an operator called me where there was third-party damage and they were putting soapy rags on a broken pipe. They'd squeezed it off. The guys got in their fire suits. One guy went in the hole and the other guy out outside the hole, but they didn't put their helmets on because it was a hot day. Sure enough, it flashed and both of them went to the emergency room. If you establish these procedures, they're only as good as your enforcement of them. You need to be ruthless in your enforcement of your procedures. The second aspect of static electricity in polyethylene pipe is electrostatic pinholing. Most people, when they think about static electricity in polyethylene pipe, only think about the ignition risk that static creates in polyethylene pipe. But in reality, it's been documented that static electricity puts holes in polyethylene pipe. So the first thing is to define what is an electrostatic pinhole. It is defined as a hole in the pipe wall created when the friction of the gas passing inside the pipe reaches a voltage high enough that it exceeds the dielectric or insulating strength of the pipe wall. That static charge arcs through the pipe wall to the surrounding earth, grounding itself. The heat from this arcing melts the plastic in its path, creating a hole. This next slide is an electron microscope section of an electrostatic pinhole in a piece of polyethylene pipe. And you notice it almost looks like a miniature lightning bolt. And essentially that's what it is. That static charge has gotten so high, the friction has created a static charge so high on the inside of the pipe that it has overcome the ability of the plastic to resist its movement. And it arcs through the plastic pipe to the ground surrounding itself. And the heat of the arcing of the electricity, the static electricity, melts the plastic and creates a hole in the pipe. This has been documented by your gas research company. Here's what they say. The charge conditions across the pipe wall can increase high enough to exceed the material breakdown. This breakdown phenomenon produces a small burned hole about the size of a pinhole through the pipe wall that can leak minute quantities of gas. So the first thing to understand about static electricity and pinholing in polyethylene pipe is that the passage of gas inside pipes, pinholes can be created during the normal operation of gas passage inside a pipe. That's what your gas research company is saying. They say, even under apparently normal operations, when the pipe is not being squeezed, pinholing is observable because of the high turbulent flow conditions occurring near T's, elbows, etc. So you can have a situation in the normal passage of gas that the friction inside the pipe, even though it's not exposed to ground, opened and creates an ignition risk, can arc through the pipe walls and create a hole leaking minute quantities of gas. Now, you're not in the business, and the gas distribution industry is not in the business of chasing down pinhole leaks. But the problem is you can have accumulations of pinhole leaks in areas where static is building up inside of the pipe to the point that it creates a fire hazard, or you get repeated leak calls because of the accumulation of numerous pinhole leaks. This next slide that you're going to see was sent to me by Fire Findings newsletter. It's a newsletter subscribed to by fire investigators in their forensic research to determine the cause of fires. And they were finding a number of fires at gas meters, and they had no known ignition source. And they called me and were asking me the question, could pinhole leaks cause this meter fire? And the answer is yes. We've had operators tell us where they'll get service calls from house owners, and they will come from the street, and as they're walking along the street, they'll look down and see brown grass, and then 3 feet later brown grass, and 3 feet later another brown grass. And what's happened is when they dig it up, the service line has numerous pinhole leaks, and they're all caused by static electricity. The average person, the average operator, believes that these pinhole leaks are due to manufacturing defects in the polyethylene pipe. In all the cases that we've been called into where there's been excessive pinhole leaks in lines that cause their repeated replacement, and the pipe has been sent to a lab, 100% of the time the lab has determined that it was electrostatic pinholing, static electricity, and not manufacturing defects that caused the holes in the pipe. And it makes sense because when you put in a pipe, if it has a manufacturing defect, it wouldn't pass a pressure test when you install it. All these lines that later had leaks in them because of pinholes pass pressure tests when they are installed. So it's important for you to be aware that static electricity can cause pinhole leaks in pipes. And if you are, as an operator, having to repeatedly replace pinhole pipes in areas because of excessive leaks, if you keep replacing them and don't do any static mitigation, the pipes are simply going to pinhole again. Static electricity is the cause of these leaks, so unless you do interior static suppression, you will not stop the replacement of these pipes. These pipes will continue to pinhole, and you'll be continually replacing them. This next slide is a picture of our Ionix static suppression cartridge, and it's installed in a filter housing. We make a static suppression cartridge. It's put in the gas line, and what it will do is it dissipates the static inside the gas pipeline from the point of introduction to the burner tip. And we've had numerous customers who have installed this at their gate stations to dissipate static downstream where they were having pinholing of their service lines. So if you're having pinholing occurring in service lines to the point that you're getting numerous leak calls and having to replace these lines with new lines because of pinhole leaks, you need to consider putting interior static suppression in order to stop this problem. Our experience has shown there's certain characteristics of electrostatic pinholing in polyethylene pipe. First of all, that most pinholes are occurring in 1 inch or smaller plastic service lines. There doesn't seem to be any pattern in the number of pinholes in a pipe. We've seen a pipe that has had 1, 2, 3, 4, 5 pinholes in it. We've only seen it in polyethylene pipe. We have not had any reports of it in PVC pipe. We have seen it in all manufacturers' brands of pipe. We had one customer who had a line where he had 3 different manufacturer brand of pipe in this service line, and every single piece of pipe had a pinhole in it. So it is not a problem that is solely due to a particular brand of polyethylene pipe. And it has a tendency to cluster in areas. If you have a problem with pinholing, excessive pinholing in service lines in an area, you're going to have it in that whole area. I can't tell you why it occurs in a certain area. We just know it seems to have is concentrated in geographic areas. As we conclude this video about static electricity and polyethylene gas pipe, I'd like to leave you with one final thought about pipeline safety. Pipeline safety regulations are designed to protect the public and to protect our workers. But there's also the perception of natural gas as an energy choice, which is an important consideration in your operation of your pipelines. My son-in-law works at the McGuire nuclear power plant of Duke Energy in North Carolina. They can generate nuclear-powered electricity for 2 cents a kilowatt hour. The average wholesale price in the United States is 12 cents a kilowatt hour. You would think then that we would start building nuclear power plants left and right because it's so cheap to make electricity. But there's no consumer confidence in the generation of electrical power using nuclear means. Malaysian Airlines lost an airline over the Indian Ocean. And several months after that, one of their airliners got shot down over the Ukraine with all loss of life. The bookings dropped on that airline, and several months after the second incident, they had to lay off a third of their workforce because there was no consumer confidence in the safety of that airline's transportation of passengers. The purpose of pipeline safety is to build consumer confidence in the choice of natural gas as an energy source by consumers. If they're not confident in the safety of the product, they will vote with their feet, just like they do with the Malaysian Airlines, just like they do with nuclear energy. It's important that your gas company not wind up on the evening news because of an incident where somebody was hurt or there was a pipeline explosion. It's important to deal with this so that we build consumer confidence in natural gas as a consumer's energy choice. Because those consumers in the purchase of natural gas will pay your salaries, they're going to fund your benefits, and they're going to pay for your retirement. And so it's important that we make consumers feel confident in the safe delivery of natural gas in our systems. I hope this video has given you the basis to understand how you can prevent static ignitions in your systems. If you have any questions about static, please feel free to call us. If you need some help in generating procedures or you have questions whether a procedure you have is effective, feel free to call us. We'll be happy to answer any questions you have. You can go to our website and look at our products, our aerosol static suppressor for dissipating static on the outside of the plastic pipe, and our reach tool that allows remote dissipation of static, and then our cartridges that suppress static inside plastic pipe systems. Our contact information is at the end of this video. Thank you very much for watching this video.